Hello students, we are into Expt Astable Multivibrator. Again, you can download this document from this link provided. So here is the disclaimer. This is the outline that we are going to follow for our presentation. Now, an Astable multivibrator has no stable states. Once the multivibrator is on, it just changes its states on its own after a certain time period, which is determined by in this case, for this particular circuit diagram, it is decided by the timing constant of C1 R3 and C2 R2. We also require a VCC for the operation of this transistor circuit, and as far as the construction is concerned, it consists of two transistors Q1 and Q2. Connected in a feedback arrangement with one another. The collector of transistor Q1, so here is the transistor Q1, this is the collector terminal. The collector of transistor Q1 is connected to the base of transistor Q2 via this capacitor C1, and the collector of transistor Q2 is connected to the base of transistor Q1 via this capacitor C2. We can derive the output from both the ends, from VC1, that is VO1, or VC2, VO2. Again, they will be out of phase with one another. The emitters of both the transistors are connected to ground. The collector load resistors for this circuit, that is R1 and R4, and the biasing resistors R3 and R2 are typically of equal values. So is the case with C1 and C2. Now let us try to understand the working of this circuit. Let us assume we are applying a voltage of 6 volts VCC, and second assumption that we'll consider here is the transistor Q1 has switched off. So these are the assumptions to begin with. Transistor Q1 is switched off and VCC is 6 volt. So if this is the case, then its collector voltage is rising towards VCC. So Q1 is switched off, meaning it is not conducting any current, so the voltage here will rise towards the value of VCC. Meanwhile, the transistor Q2 is turned on. So this is one stable state. Q2 is on. Now look here, there is capacitor C1, and let us mark the two plates as A and B. Now the plate of capacitor C1, that is plate A, is also rising towards the plus 6 volts supply from VCC, as it is connected to the collector of Q1, which is cut off, and since Q1 is cut off, it will not conduct any current, so there will be no voltage drop across R1. I hope this is clear. The other side of the capacitor is marked as B, so this is plate B, which is connected to the base of transistor Q2, and we have said that assumption transistor Q2 is on, so the base emitter voltage will be 0.6. so the voltage at this plate will be 0.6, because this transistor is on, it is conducting, it is in the saturation mode. This implies that the capacitor C1 has a potential difference of plus 5.4 volts across plates A and B of capacitor C1. So if I travel from point A to B, there is a voltage drop of plus 5.4 volt. And how did I get this value? It is 6 volts minus 0.6 volts at the base of transistor Q2. Since Q2 is fully on, C2 starts to charge through R2, towards the value of VCC. So this is on, so this capacitor will start to charge once this path is completed, VCC through R2, C2 to through transistor Q2. So when the voltage across capacitor C2 rises to more than 0.6 volt, it biases the transistor Q1 into conduction, that is saturation. So I hope this is clear. Moment this voltage across capacitor C2 charges to 0.6 volt, fine, it will make this device, that is transistor Q1, to on. So it will start conducting. The instant that Q1 switches on, the plate A of the capacitor, which was originally at 6 volt, okay, VCC potential, immediately it falls to 0.6 because this is conducting 0.6 volt, and this rapid fall of voltage on plate A, okay, it causes an equal and instantaneous fall in the voltage on plate B. So therefore plate B of C1 is pulled down to minus 5.4 volts, okay, a reverse charge, and this negative voltage swing is applied to the base of transistor Q2, so turning it off. So this is the next state. Initially we had assumed it to be as on. Now because of this action, the transistor is driven to cut off. Now since this transistor is driven to cut off, so now this capacitor C1 begins to charge in the opposite direction via resistor R3 because this is conducting. So it will start charging through this path because this is connected to a VCC of 6 volts. Thus the base of transistor Q2 is now moving towards a positive direction. So the voltage at this plate is now going to build up, fine, and will it is rising towards a value of VCC with a time constant equal to R3 and C1. This product of C1 and R3 will decide the timing intervals. However, it never reaches the value of VCC because as soon as this voltage, okay, reaches a value of 0.6 volts positive, look here, the moment this voltage reaches to 0.6 volt, where this voltage is connected, it is in turn connected to the base of transistor Q2, which is off. So the moment a 0.6 voltage is available to the base of transistor Q1, what will happen is that this transistor Q2 will driven to on condition, that is a saturation. This transistor Q2 turns fully on. Now this action starts the whole process over again, but now with the capacitor C2, okay, taking the base of transistor Q1 to minus 5.4 volts, thus entering the second unstable state. So basically there are no stable state, okay, both are quasi-stable state. In one state Q1 is on, Q2 is off, okay, and the second state this is off and this transistor is on. So if I connect the LEDs across these two in line with these two wires, we are going to have a flickering effect. So thus we can say that this circuit alternates between the two transistor states, Q1 on, then Q2 is off, and the next instant when Q1 is off, Q2 will be on. Now as far as this timing interval is concerned, periodic time, total time t equals to t1 plus t2, and this timing interval t1 is equal to 0.69 into C1 R3 and T2 equals to 0.69 C2 R2. Now these equations are with respect to this circuit diagram. If C1 equals to C2 equals to C and R2 equals to R3 equals to R, okay, then we can calculate the frequency of operation, that is oscillation, equals to 1 by T, that is 1 upon 1.38 RC. Now if I want to vary the frequency, it all depends upon the value of R and C. And what is R and C? These are the components C1, C2 and R2, R3. Nowhere you see the term VCC appearing here, and R1 and R4. So the timing depends upon the product of C1, R3 and C2, R2. Okay. Another thing is R is expressed in terms of ohms, capacitor in terms of farads, and frequency in terms of hertz. Now what if I want to change the frequency? I have to either change the value of R or C accordingly. So if I want to set a design like this circuit should generate an output of say 1 kilohertz, so frequency set it to 1 kilohertz, then you can assume the value of C to be as say 10 microfarad and calculate the value of R. and when you mount this value of R and C, let us say this X and 10 microfarad in this circuit, hopefully you should get a output of 1 kilohertz. Follow? Multi meaning many, vibrator meaning oscillator. So we can generate the frequencies of varying frequency here by varying the components. So this is all about the theoretical background. We have already uploaded a lecture on analysis and design of basic Astable Multivibrator. You can go to this link, or you can click on the I button and you can go through that this video. Okay, it is lecture number 43 of our regular course in electronic devices and circuits for RC 2019-20. So aim of this experiment is to study the operation and observe the waveforms of Astable Multivibrator, and as I've said, like, we can get the output at both the ends, here as well as here. So we can tap the output signal from both the collectors, but the thing is, for example, at one timing interval, if this is high, for that corresponding time interval, the output of V02 will be low, and when this is low for the second half, it will be high for this corresponding time interval. So they are just inverted to each other. And then theoretically you can design a stable multivibrator. So you have the frequency equation with you. It is 1 upon 1.38 RC. This is theoretical part. Okay, take F equals to 1 kilohertz. Then you can assume the value of C, okay, some 0.1 microfarad or 10 microfarad, and you find out the value of R. So this will complete our design, and hopefully we should get a frequency of 1 kilohertz. These are the components required: transistor BC107, regulated power supply. These are the resistors. Again, as I said, the value of resistors depends upon the design of intended frequency of operation. If your frequency is changed, the value of resistors will definitely get changed. So again, for the capacitors, then we do require CRO to observe the output waveforms, breadboard to mount the circuits, multimeter to check out the readings, and connecting wires to connect the components. Here is the circuit layout. I have just interchanged the notations here. These notations are used here are different from the one which I have explained for the theoretical background. In the practical write-up, I have used this circuit diagram. So you see C1 and C2 equal to 0.1 microfarad, RC1 and RC2 is 1 kilo ohms, and both R1 and R2 are of same value, 10 kilo ohms. Okay, so this is not required. And always without fail, you have to encircle the transistor. So you have two transistors, Q1 and Q2. I can take the output at VC1 as well as VC2. So now a CRO, okay, this is a display. It has two channels, channel A and channel B. Now there are two cases you have to observe two waveforms. First case 1, output at VC2, and B, output at VC1. So you take this channel A and channel B, and you connect across VC1 and VC2. Okay, you are going to observe the signals which are opposite in polarity. Fine. And the second case, channel A, you connect it to the output of, say, VC2, and channel B you connect to the input terminal at VB2. Okay, so you connect the CRO channel 2 at base terminal and CRO channel A at this terminal, collector terminal. Okay, you are going to get a separate waveforms. So this is a design. You can go through. This is 10 to the power minus 3, 10 to the power minus 6, and here any more changes. This has to be IC max. Okay, fine. This is some regular typos. Okay, this is the voltage across the base 1, and here the output, this is the output across VC1. Fine. So when the transistor Q1 is on, output will be 0. When the transistor Q1 is off, output will be high. So this you have to observe, and this you have to plot on a graph sheet. Fine. And another most important thing is you have to note down the voltages. This will be 0.6, this will be VCC. Now in our case we have applied a VCC of 12 volts. Fine. And for expansion I have taken it to be 6 volt. So I hope this is clear to everyone. Waveforms are most important thing. Precautions, again, just like for last 2-3 experiment we have been categorically saying that the 3 terminals of the transistor should be carefully identified, because each terminal has got a different function to perform. We simply cannot interchange. All the connections should be correct, and verify the gain of the transistor amplifier circuit. How do we verify that the transistor circuit is working? Just connect a function generator with a signal of 20 millivolts and a frequency of 1 kilohertz. We should get us output. Fine. Or you can check out the output voltage using a multimeter. Make sure that transistor circuit is working, because it's basically 2 transistor switches connected back to back. Fine. And hopefully when you mount this circuit, you should not have any problem. The results: an Astable Multivibrator is designed, the waveforms are observed and verified, the results theoretically, and here you have to mention the values. Okay, what are the timing intervals, what is the amplitude, what is the frequency, all those things should be mentioned here, all the quantitative analysis. And then we have set out some questions in the aim. Okay, so those questions have to be answered here. Conclusion: finally what you have concluded after performing this experiment, that's more important. And these are some of the questions which definitely will be discussing during our online sessions, and this will carry marks. So I request all the students to go through this Viva Voce questions and prepare yourself. So questions will be mostly 80% of the time will be limited to these questions, Viva Voce questions. So make sure that you go through these presentations. Also online video classes has been uploaded. Go through those classes, lectures, and we do have so many online resources, textbooks. Go through it, try to find out the answers for all these questions. Fine. And for write-up of this experiment, you can visit this link. Okay, just assignment batch wise, and make sure that you don't plagiarize, you don't copy from others. Maintain the originality. Okay, now we will start with the demonstration video.
Okay. Hi friends, in this video we will be learning about how to build a Astable Multivibrator circuit. Okay, as you can see in this figure, it has 2 identical transistors. Okay, and output of one transistor is given as input to the other transistor, and output of the other transistor is given as input of the other transistor over here, as you can see in the figure. Now if you want a proper square wave for this Astable Multivibrator, okay, you have to have a symmetrical circuit in which R1 should be equal to R2 and C1 should be equal to C2. Okay, and so like this arrangement you have to do. Now the formula for this particular circuit is, for time it is T is equal to 1.38 RC. Okay, now here we have taken R equal to 10 kilo ohms and C is equal to 0.1 microfarad. Okay, and then we substituted these 2 values in this particular formula, and then we tried to find out the frequency. So frequency is 1 by time, that is equal to 724.63 hertz. Okay, so this is the theoretical frequency for Astable Multivibrator that we are designing today. Okay, theory is already explained. Okay, now the first thing what I told you all is in my last video also, it is always good if you select your components and place it in your circuit. So we require 2 10 kilo ohm resistors. So I will place one 10 kilo ohm resistor here and 10 kilo ohm resistor here. Okay, and 2 1 kilo ohm resistors. Okay, so 1 kilo ohm resistor here and then 1 kilo ohm resistor here, and then we need 2 0.1 microfarad capacitors. So these are the 2 capacitors. Okay, so this is what it is. Okay, and we require 2 transistors. Okay, for this experiment we are using SL100. So I'll be just keeping this 2 transistor here. Now it is very simple. Okay, now this is the SL100 transistor. Now you just see transistor has emitter, base and collector, so you need to find out which is emitter, base and collector. So you can see a notch here, you can see a notch here. Okay, so on this side of the notch, this is emitter and this is base, okay, and then this is collector. Okay, so from this notch you have to see, okay, emitter, base and collector. Okay, so you have to mount your circuit as per the diagram on the breadboard. Okay. Okay, so first we'll take the transistor. So this is emitter, this is base and this is collector. So what we'll do is we'll set it up like this. So I'm just putting in this is breadboard. Okay. So collect emitter, base and collector. Okay, same we'll put it over here. Okay, so it is emitter, base and collector. Okay, now just see, now we have just two collectors over here. So we have 1 kilo ohm connected to the collector. So I'll just put 1 kilo ohm resistor here and 1 kilo ohm resistor here. Okay, and then I will just connect it. This I will make VCC. Okay, so this is one. Okay, then we have two 10 kilo ohm resistors. So I'll just put it somewhere here. Okay, so this is how I have arranged it. Okay, next is I need to put this capacitor. Okay, this capacitor. So it has to be in the collector. Yes, this is one is done, and here also I'll be placing it here. Okay, so this section is done. Okay, now what you need to do is you have to connect output of this to the base of this. Okay, so you need a wire. Okay, now we have assembled the circuit. Okay, now we have this power supply. Okay, first I'll explain what I have done. Now this is the negative. So what I have done here, you can see both the emitters are grounded. So I have connected a wire from this emitter to the other emitter. Okay, and then they are connected to negative. See, okay, so this is a negative. So this wire is actually grounding the two emitters. Okay, and then it is connected to the negative of the power supply. Positive is connected to this. Okay, now what I will do is that I will connect this to the collector, this wire to the collector of the transistor. So what I have done is that I want to I have used two BNC probes. Okay, what I am trying to do is that I want to measure the waveform, or I want to see the waveform at this point as well as at this point, both the points. Okay, so both the collectors I have connected the CRO probe. So I have used CRO here. The first will set the power supply, so we need to turn it on. Okay, and then we need to set this to around 12 volts. Okay, so around 12 volts we have to set it up. Okay, okay, so 12 volts we have set it up. Now I have used CRO here. I have used both the channels. Okay, one channel is actually showing you the output of this transistor, the one transistor, and the other channel is showing you the output of the other transistor. Okay. What? Okay, now we already had this formula for time t equal to 1.38 RC, and we had put 10 kilo ohm and 0.1 microfarad for the capacitor, and then we found out that the theoretical frequency is around 724.63 hertz. Okay, now we'll actually see what frequency we are getting at the output. Now you just select any one of these because both outputs are same. So if you select this, so it is around 1, 2 and 2.5 divisions, almost around 2.5 divisions. So 2.5 into 0.5, that will give you your time base. Okay, so T is equal to, so T, this is practical, okay, practical, okay, frequency. As per your waveform, we are getting 2.5 divisions into, what is the time base? 0.5 milliseconds. That is equal to, okay. So from the CRO we have found out that the time for one cycle is around this. Okay, so 2.5 divisions into 0.5. Okay, I'll just show you once again. So it is 1, 2, 2.5 or 2.5 into 0.5 milliseconds. So this will be your time. Okay, this will be your time. So if you see here in this formula, if you substitute T equal to 2.5 into 0.5 millisecond. So what is frequency? Frequency is around 1 by T. Okay, that is 1 by this value, that is 2.5 into 0.5 millisecond, and it is giving you a frequency of around 800 hertz. Okay, so this is the practical frequency that we have obtained from this particular design. Okay, and expected frequency was 724.63 hertz. Okay, so this was a theoretical frequency, and this is your practical frequency. Okay, so this is one thing that you should know. Next thing, see, now what we have done is that we have taken waveform across this point and this point. So what we'll do is that we'll take waveform at this point. We'll see what happens at the collector and what happens to the base. Okay, so what I will do is that I will remove the this probe from this collector. Okay, and then we'll connect it to the base. Okay, so just see at the output what is happening. I'm just connecting it to the base. Okay, just connect it to the base, sorry. Okay, so this is, okay, so this waveform is at the base of that particular transistor. Okay, and this is at the collector of the transistor. Okay, so you should be understanding this properly. Okay, why it is so. Okay, so thank you very much.